RC is 2K. Here GM is alpha by RE. Alpha is beta by beta plus 1. Here, after getting the gain, V0 is nothing but V0 peak to peak is 2 of ICQ R. Here ICQ is nothing but GM into VT. So here R is nothing but RC. So after substituting all these derivations, means whatever the values we have, we are going to get V input peak to peak swing is 80 millivolts. Here options are 40 millivolts, 60 millivolts, 80 millivolts, 100 millivolts. Hence option C is correct.
He has given a transformer secondary terminals connected with a load which is drawing 20 amperes at 0.8 power factor. And for this 20 amperes 0.8 power factor load, the losses are 20 watts. And we have to find losses at 0.6 power factor lagging when same amount of load current is drawing at the secondary terminals of a transformer. Okay. Now if you see here, the loss P loss, that is, it is nothing but a loss in load, is power dissipated. Okay, power dissipated is Vi cos phi, or you can write as this one as, since V is equal to Iz, okay, since V is equal to Iz, this is into I, cos phi is R by Z. I can write this one as I square or watts. Okay, or else I can write it as Vi cos phi. Okay, now what is Vi cos phi? He has given losses which is equal to 20 watts and load is drawing 20 amperes. Cos phi is power factor which is equal to 0.8 lagging. Okay, this is equal to 20 watts. Now what is voltage here? V is equal to 1.25 volts. Similarly, we have to find when load is taking 20 amperes, okay, and voltage is 1.25 volts. You can write this one as V2. 1.25 into 20 into at 0.8 power factor lagging, which is equal to 15 watts. So option is C.
For a unity feedback system, G of S equals to 200 by S into S plus 8 and R of T equals to 2T. To reduce the steady state error by 5%, the new value of gain is, we know the steady state error ESS is given as limit S tends to 0 S into R of S by 1 plus G of S H of S. Here R of S is equals to 2 by S square, which is 2t, the Laplace transform of 2t. H of S equals to 1. So ESS equals to 2 divided by 1 plus limit S tends to 0 S G of S. This is 0, so this one. So which is 2 by kV. kV is nothing but limit S tends to 0 S G of S. So which is equals to 200 by 8, which is equals to 25. So ESS equals to 2 by 25, which is equals to 0.08. So if we reduce the steady state error by 5%, means the new steady state error is equals to, this is the new one after reducing, equals to ESS minus 5% means 5 by 100 into ESS, which is equals to 0.076. So now the new steady state error is given as 2 by limit S tends to 0 as K by S into S plus 8 is equals to 0.076. Means if we solve this equation, we will get a K K as 210.52, which is option B is correct.
A 0 to 300 volts voltmeter. Okay, he has given a voltmeter, starts from 0 and full scale deflection is 300 volts. It is having an error of 2% on full scale deflection. If the true voltage is 30 volts, that means meter is measuring 30 volts. So what is the range of this voltmeter would be? Okay. Now, if you see here on full scale deflection, this voltmeter is having 2% error. Okay, that is 300 into 2 by 100, that is plus or minus 6 volts. Now for 30 volts on full scale deflection, now the full scale deflection is 30 volts. Okay, this is 30 plus or minus 6 volts. Okay, 30 plus or minus 6 volts. The reading of the voltmeter would be 24 to 36 volts. Answer is option B.
Question is in the figure below, L1 equals to L2 equals to 2 henries, R1 equals to R2 equals to 10 ohms, I0 equals to 5 amps. If RL equals to 1 ohm, find the drop across the RL at t equals to 0 plus, following the opening of the switch at t equals to 0. Assume steady state before switching. See, at t equals to 0 plus, we need to draw the diagram. So at t equals to 0 minus, at t equals to 0 minus, IL2 of 0 minus equals to 2.5 amps. IL1 of 0 minus also 2.5 amps, because the resistances R1 and R2 are equal. In the steady state condition, L1 and L2 acts as a short circuit. So I0 is equally divided between R1 and R2. So the magnitude of I0 is 5 amps. Hence, the IL2 of 0 minus is 2.5. IL1 of 0 minus equals to 2.5. So at t equals to 0 plus, IL2 of 0 plus equals to IL2 of 0 minus, which is equals to 2.5 amps. Hence, the voltage across the load resistor at t equal to 0 plus is equal to 2.5 volts, which is option C is correct.
Now find V2 of the non-planar network. Okay, it is shown below. Now where is V2 here? V2 is in this branch. Okay, voltage across this branch. Now how to find V2? Okay, just a simple law, KVL. Okay, what KVL says? KVL is voltage in a closed loop is equal to 0. Now apply KVL in this loop. V2 minus 2 minus 4 is equal to 0, or you can write as minus V2 plus 2 and plus 4 is equal to 0. You will get V2 is equal to 6 volts. Suppose we asked V1. Now what is V1? V1 minus 1 minus V2 is equal to 0. Now what is V1 here? V1 is equal to 7 volts. Okay, this is simple KVL law you have to apply. Answer is, we have to find V2, so answer is 6 volts.